morning, good afternoon, good evening, wherever you're joining us from. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I would like to welcome you to today's MEPTEC IMAPS Semiconductor Industry Speakers Series presentation. The next presentation in the series will be on Wednesday, March 31st, 3 weeks from now, so a slight change to our normal pattern. Thomas J. Green from TJ Green Associates will talk about mil-spec hermeticity testing of Class 3 medical implants. So he will discuss the challenges of making sure you get a medical device right. So it's a long-term reliable device. So that should be a fascinating presentation. So please join us for March 31st. And then we will have presentations in April, and we will announce those shortly. The webinars start at 11:30 a.m. Pacific time, run approximately an hour. If you're interested in speaking at a future webinar, please let myself know or Dave Town, and we're more than happy to have all kinds of appropriate presentations. So thank you for your submissions, and we look forward to hearing them at a future Semiconductor Speaker Series event. In terms of MEPTEC, we are a membership and sponsorship supported organization. That is what makes events like today available for free to everyone. So if you haven't renewed or joined, please do so. Or if your company is in the position to sponsor, please reach out to us. We'd love to have you. If you have questions, please reach out to Betty B. Cooper at meptec.org, and she'll certainly take care of you and give you the information you need. So thank you for your support. So today's Semiconductor Industry Speaker Series presenter will be John Park. John is going to be presenting an EDA perspective. What's the difference between heterogeneous integration and system in package? John is the Product Management Group Director for the Advanced Semiconductor Packaging team at Cadence Design System. They work on cross-domain solutions across integrated circuits, packaging, and printed circuit boards for co-design and analysis. He is a frequent author and speaker at many events, and he's clearly a recognized expert in this area. So I'm very happy to welcome John.
Thank you, Ira. As Ira said, what we're going to be talking about today is really start to put down some definitions between some terms that are being thrown around these days, terms such as chiplets, heterogeneous integration, 3D stacking, those types of things. There's no real good definition for a lot of these new technologies, and I'm going to try and outline a few concepts and ideas of how I see the kind of the convergence between the system and package world, which we've been in for 25 years, and this new world of heterogeneous integration. So the outline that I have for today is broken into 4 sections. We'll start off and jump right into a definition of a possible definition of the differences and similarities with SIP versus heterogeneous integration. We'll then talk about why heterogeneous integration is happening, what's driving it, the primary factors behind all that. And then we'll talk a little bit about some of the design challenges that we see when we at Cadence talk to our customers, some of the challenges they see from both a package designer's perspective and a chip designer's perspective. So again, we won't go into too many gory details due to the limited time frame that we have today, but we will talk about some of the high level challenges there. And then I have a few slides talking about some potential flows and methodologies to help bridge the gap or get across or get through those challenges. And we'll wrap up with a slide on talking about a summary and some conclusions. So let's jump right into what is SIP and what is heterogeneous integration, and a definition of each one of those. So This is a slide I use a lot. It's a timeline, not going back too far, back to the mid 90s or so, up in extending into the future of the different types of multi-chip packaging that's going on there. It's not a comprehensive list, but covers a lot of the big trends in packaging. And as shown here, the system and package world, which is generically speaking, oftentimes a heterogeneously integrated system with different dies across different technologies and across different nodes. And how is that different from the definition that we're using today, which is more to the right side of this picture, really talking to, kind of bringing this term heterogeneous integration into play. And that's what we're going to be talking about, is that, both of those work with multiple devices. They're the integration of different semiconductors, but what is really the difference between those? Because a lot of people kind of interchange those different terms, and I think it's important to get a definition down. So let's jump right into, at least in my mind, a pretty succinct definition that kind of talks about SIP and then talks about heterogeneous integration. So we're going to start on the left-hand side of the graphic here, and we start with a PCB. And what we've been seeing over the last, even with beyond SIP, with multi-chip modules, so 4 or 5 decades now, we've seen this trend towards taking bare die out of their packages and taking them, and either whether they're mounted with wire bond attach or flip chip attach, and then reintegrating those bare die onto typically a laminate substrate, sometimes a ceramic substrate, and then really kind of doing all the die to die interconnect there. There's lots of good reasons for this. It makes you take and take the die out, and you're able to place them closer together, so you end up with a smaller footprint, less power, because you don't have to go through all the packaging interconnect. And so there's a lot of good reasons, and it was initially driven under this term SWAP, size, weight, and power, which is important to the defense industrial base. So multi-chip module, system and package, at least in my definition, is really about the simplification, streamlining, improving the performance of a PCB. So that's kind of the left-hand side of this picture. And certainly these bare die are often different process nodes and different technologies. So generically speaking, you could call that heterogeneous integration, but that's not how the term's being used today. It's being used with the right-hand side of this diagram. So what we see happening here is, instead of simplifying the board, we're actually looking at a system on a chip or some sort of ASIC and looking at different ways to build that chip. And we'll get into why people are doing this in the next several slides. But the term heterogeneous integration now is really being used to talk about disaggregated SoCs or modularized SoCs, and really kind of taking the IP and creating this new block, this new concept called a chiplet, and then building those chiplets at different nodes, different technologies, and then reintegrating them together, typically on a silicon substrate, sometimes glass. There's people looking at laminate, but in general, the integration platform is typically a silicon substrate for a lot of these designs. So we're going to talk a little bit more about the details here, but from a high level definition, this is how I think is a reasonable way to define things. So taking a board and making it converting it into a package is system and package, and taking a chip, a monolithic SoC, and building some sort of package out of that is, I think, how the term heterogeneous integration is being used today. So with that as kind of the high level, the title of the slide was really talking about what the differences are here. We're jumped right into a definition of kind of the different worlds and how the different terms are being used. So a little bit more about heterogeneous integration. As I said, it's typically taking blocks of IP, building them separately and then aggregating them onto some sort of platform, typically silicon these days. But the way to think about this heterogeneous integration is, and I think is an important thing, is that it's independent of the packaging. It has nothing to do with packaging. I can integrate multiple chiplets on a silicon substrate, on a high density RDL, on glass, on lots of different ways. I can 3D, I can stack them, in the third dimension, lots of different things. So the idea of heterogeneous integration is really a way to logically partition a design in a different way. So it's about the logical partition change, not about the packaging. When we talk about heterogeneous integration, because there is no standard for integrating all of these chiplets together. At least there's no standard today. So I think that's an important thing to understand, is the heterogeneous integration can be separated from terms like 3D IC and CoWoS and fan-out wafer level packaging. Those are packaging technologies. They're not logical partitioning or different ways of logically partitioning a system or subsystem. So what's happening today is a lot of people have looked to SIP because, with SIP, we'll talk more about this. We've been doing a lot of these things. We've been doing heterogeneous integration. We've been doing 3D stacking and those types of things. But the idea is we're now taking this SoC, breaking it into multiple pieces. We'll talk about a little bit more about what chiplets are, but in our view, it's just a third flavor of IP. So one of the big driving factors of SoC design, system on a chip design, is reuse based on different intellectual property. So different blocks of silicon from all the IP providers out there help you to build an SoC. Just add your special sauce to that, and so it's a key to creating successful system on chip type applications. And the way we see it, chiplets is just becomes a third option to IP. And in the case of a chiplet, it's actually something that's been built. It's got little micro buffers around it to be able to communicate some standard, based on some standard communication bus between other chiplets on the design. And it has things like level shifting, so you can work across different voltages and maybe some test and ESD and those types of things. So it's actually a built versus hard versus soft is basically a GDS of the IP. Soft is more RTL type of description, and you can implement it yourself. A chiplet, in our view, is a physically realized block of IP. So hopefully those two slides kind of give a high level understanding for some people about the differences between chips and chiplets and heterogeneous integration and SIP. So a little kind of a summary slide here of SIP versus heterogeneous integration. On the left is system and package. And as I said, it's really about the simplification, performance improvements of a PCB. So you're taking things out of their packages, integrating them onto a single device. You can place them closer together, and you have less power, shorter signal paths, so you can improve performance. Those types of things. The system and package applications are mostly schematic driven, so almost like PCB types of design flows. And of course, we have different ways of attaching the bare die. Historically, mostly wire bond attached, but more recently, a lot more flip chip attachment of those designs. And they're flip chip attached. The bumps are, anywhere from kind of 110 microns up to 180 microns, and even a little bigger than that. The typical laminate substrate or laminate substrates in build-up substrates can handle that pitch, so we're good there. And we've been 3D stacking bond wire attached dies for some time now. And as I said, most of these are done on laminate, or what some people call organic substrates, and a little bit on ceramic. So all that I think makes good sense. The only challenge you introduce from moving to a system package, the biggest challenge I should say, is your thermal. You need to take a closer look at thermal because you're putting devices much more closer together inside of a package. But there's a lot of positives that outweigh that bigger challenge with thermal. If we move over to heterogeneous integration on the right-hand side here, as I said, this is about the disaggregation or modularization of an SoC. It's really done to, in some ways, to reduce cost, to improve turnaround time, and really to provide a more flexible way of building system level architectures for designs. The people that are doing heterogeneous integration come from a chip world, so it's mostly text or language based types of design flows that they put together. They're used to coming from a world that's all about timing, especially on the digital side of things. And so there's some big changes, big differences that we're going to talk about that happen when you move to this this heterogeneous integration world. But the biggest thing that throws people off is we've spent the last decade plus focused on PPA, power performance and area. If you're designing SoC, that term PPA is used, constantly, because that's what you're trying to achieve when designing an SoC. And it seems like we're kind of throwing that out the window when we go to heterogeneous integration, because area, it's going to be bigger because we have multiple chiplets. They each have their own IO buffers. So, unless we start 3D stacking, the form factor is going to be bigger, definitely in an X, Y coordinate and in the Z coordinate if you do start stacking. So you end up with longer signal paths, more IOs, larger form factor. Those don't seem like good things if you're used to designing SoCs. That's the opposite of what you've been focused on for the last decade plus. So that's what we're going to be talking about next, is why would you want to do that? Why would you want to, take things and that are really small and actually make them bigger? Because higher, more power consumption, higher, larger form factor, lots of bad things happen. So why are people doing these heterogeneous integrated architectures? So let's talk about, before we talk about kind of what's driving this trend towards heterogeneous integration, any questions about the last 3 or 4 slides?
Yeah, there's one question here from the audience. And, their packaging technology has a dependence on the die-to-die interface choice. And it was just a general question. Maybe you're going to address it later, but do you see design houses like Cadence and Synopsys becoming chiplet vendors? I mean, you do have marketplaces for IP, and you talked about the chiplet as sort of not hard IP, but physical IP.
Yeah.
Is there a roadmap there or anything?
Yep. So I will address that within the next 5 slides.
Okay, got it. Okay.
First, we'll talk about why people are doing this, and then we'll talk about some of the challenges. And that is probably the biggest challenge, is the commercialization of chiplets. So we will definitely cover it.
Okay, and you may also be talking about the next question that came in, but it's talking about mixed signal SoC versus SiP versus heterogeneous integration. What sort of leverage do you foresee from EDA tools and perspective in designing these? I think you're going to talk about this in the design flow section.
Yep, I'll get to that in this last section here.
All right, but before we talk about it, I mean, obviously you've got the SiP as that's a packaging challenge, where the heterogeneous integration is more a design aggregation challenge.
Mm-hmm.
Is it really getting in our way that there isn't a standard definition? Because I think at the end of the day, you have to solve all the design challenges to ship your product.
Correct.
But I mean, would it make a difference, let's say, if IEEE came up with a definition?
Absolutely, it would help. And that's it's kind of a chicken egg thing between a business model and standards, right? So there has to be some progress with standards for the people that build IP to start looking at and trying to make a business case for, as you said, having an arrow or a DigiKey where I can go and look up a catalog of a chiplet and order that. So They're kind of interlinked standards and a business model, and I'm going to talk about that also. And I'll talk about you also start touching on kind of the design challenges, from a package perspective, and I'll touch on that in the third section of the talk.
Great.
All right. Okay, let's talk about why this is happening. So I think probably a lot of people on the call are aware of this, but for the few that are not, is we've been living in this world for 50 years plus. That's called Moore's Law. And Moore's Law is all about every couple of years, transistor sizes shrink dramatically, driving down the cost because I can put more functionality in a smaller space on the silicon. So it's really an economical model that said, this is going to become, economically more viable as time goes on every couple of years, because the cost per transistor will steadily go down. So that's changed. That changed a long time ago with 28 nanometers. The cost per transistor is not going down. It's not being cut in half like it was back in the olden days. And we're seeing some, kind of the beginning of the end of Moore's Law. And for some companies and some industry standard bodies, the end of Moore's Law is already here. And for others, they still talk about more. And there's certainly, a big part of the semiconductor world that's focused on that. But I think we can all agree to some degree or another that we got to start looking at an alternative to transistor scaling going forward. It's gonna, the limitations of physics are coming into play very soon. So that's what's happening. So when you're an SoC designer, ASIC designer, and there's some, you run that team and you see, the kind of the light at the end of the tunnel, or the tunnel coming up with no light and nowhere to go, you start looking for alternatives. So the interesting thing is that in Moore's paper that he wrote, or memo that he wrote, he actually predicted this on the third page of that article. He actually says it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. So I think he even, was a very smart guy. So he even kind of saw this future that we're in today, this more than more future. I think we are there today. Like I said, for many companies out there, this generation of more than more, this era of more than more is here. And for others, it's coming very, very soon. And so that's what's kind of driving the ASIC SoC semiconductor world to look for alternatives other than just leveraging Moore's Law. So, a lot of people say, well, if they're hearing this for the first time, they challenge that, and that's fair. I think we all, this slide here really is going to hopefully point out some of the factors that that kind of indicate the end or definite slowing of Moore's Law. So first of all, at some point we reached the limitations of physics down around one nanometer and below. We just can't build things that small. And as I said, ever since we went to FinFET, the cost per transistor has not scaled like historically Moore's Law says it should. And then the third bullet here is really, maybe it's saying things too simplistically, but designing something at 5 nanometers, at 3 nanometers, it's really hard, and it requires design teams of hundreds, maybe thousands of engineers. Just for the verification step, it may require 1,000 engineers just to do functional verification of an SoC. So that's expensive. The people that do that, the ASIC design community, these are not people that are standing on the corner looking for a job. It's hard to hire these people. It's expensive to hire these people, and it requires a lot of infrastructure, including EDA tools, to develop these things. And so it ends up costing a lot of money, in the hundreds of millions of dollars, to design a modern day SoC. And if you're building something like a smartphone and you are going to sell millions of that, you can recoup the NRE costs associated with that. If you're building something that's, especially something in the defense industrial base that's going maybe in a nuclear submarine and you just need 1,000 units, it's impossible to justify the NRE on that. So, and there's everybody in between that. So there are different, different amounts of pain that different companies can tolerate when it comes to cost, and it's really about the volume of the product that they're going to create. And then the fourth bullet on here, we have seen some recent examples of this is, the SoCs, these chips are becoming so big, they're reaching reticle limits. And so what that means is the manufacturing equipment can't handle it. It's too big to actually be put in without some stitching technology, which adds a lot of money. It's impossible to build it, but not many people care anyways, because these big chips don't yield. So when you start getting even close to reticle limits, your yield goes down pretty dramatically. I have an asterisk there because I'm going to explain why that happens in the next slide, or maybe the next two slides. And then of course, the world of analog and RF and to some degree mixed signal, where it's all about, you can't, analog and RF don't scale like digital does. It's not, take my transistor, make it half the size. It still does the same thing. The world of analog and certainly in RF, the world doesn't look like that. So things like I/O don't really benefit from going and chasing the latest design node. And then to kind of recertify your analog IP at a smaller node costs a lot of money. And is it really worth it? If it works at 28 nanometers, why don't you just? So these are some of the factors behind this trend of more than more and the end of Moore's law. I thought I would talk a little bit about why large chips don't yield, because as I said, a lot of people are pushing the limits of reticle size. And so this picture hopefully gives a simple example of this concept and this notion of why big chips don't yield. So these are two fake wafers sitting here, one with a bunch of big chips on it, 10 chips that could be built from that. And the wafer on the right has the potential to create 72 working chiplets. They're about half the size, the wafer on the right. And then you see little red dots, and those indicate defects. So when you build a wafer, there are always going to be defects that impact it, and those are basically they're not known good die. They don't work. They get thrown out, and that increases the cost of your chip. Is the more chips you throw out, meaning I have to make more wafers to get good chips. That's where the cost factor comes in. So having really low yield on a wafer just increases the cost exponentially, gets out of hand. So the illustration shows on the left, I've got a handful of defects there, and that's basically it basically reduces my wafer to only actually producing 10 known good die out of the thing on the left, which is a yield of about 62%. Versus the wafer on the right, I have exactly the same number of defects in exactly the same locations. However, since I'm designing a chip that's about half the size or a quarter the size, my yield goes up substantially. So now I'm able to get over 90% yield from the same exact manufacturing process with the same number of defects. I end up with a higher yielding wafer, which means my costs are going to go down associated with that. So hopefully that's a simple explanation that makes it, a little bit, helps you understand a little bit about why, why when people build these large chips, the cost is so high. It's because there's a lot of, the yield doesn't, it isn't at the same level as a smaller die. So that's one factor. And then another factor here is the fact that you got to go somewhere, most people do anyways, to have your chip actually built. And that wasn't that hard back in the early 2000s. You had a lot of different places, 26 different foundries, and this doesn't count memory, of course. So yeah, I could go to 26 different foundries that that help keep the cost down. I had a lot of different, options from where it could be built, in what country, and well, it was more competitive, and that was great. And the trend we see happening right now is fewer and fewer people, fewer and fewer fabs can afford or want to invest in the latest design nodes. So we're down to 2, maybe 3. We'll see how things go as we get down to 3 nanometers, 5 nanometers. And that just means, it's going to go up. The price will go up because there's fewer people that can build your device for you. It limits where you can build it. If you have some issues with, building certain products within a certain country, that goes away. You're basically limited to Korea and Taiwan. So it's just another component to why people are looking to heterogeneous integration or this world of more than more. So what's happening? People are looking, and it's not the first time. The chip design world, the ASIC SoC design world, is now looking to packaging to solve figure out a way around the fact that Moore's law is starting to die out. And so it makes a lot of sense to look to the world of packaging because some things aren't new, as I mentioned. So multi-die packaging across different technologies and across different nodes, been doing that for several decades there now. So we, package design community is very comfortable in that world of heterogeneous integration, using it generically, and even 3D stacking. So everyone's talking about 3D stacking now, whether it's chip on wafer, wafer on wafer, bumpless stacks, even monolithic 3D stacks. In the world of 3D is not new to package design tools or package design expertises either. We've been stacking wire bond die for 15, 20 years, and we've been putting packages on top of packages, and what we call package on package, or POP. So a lot of components, a lot of attributes that this world of more than more is looking for, we already have that capability and some of that expertise in the design community of advanced packaging. So yes, packaging 3D stacking is evolving, but that baseline of heterogeneously integrating multiple chips, stacking them vertically, some of that capability exists in the packaging world, and that's why we're looking to that. So the question came up, well, what are the challenges for chiplets, or what needs to happen? Who's going to provide these chiplets? And I'll cover that in this slide. So this all, may sound good to a lot of people, this world of chiplets, but it's not quite there yet. And one of the biggest missing components is the fact that it's all this world of chiplets is based on a closed ecosystem. It's all being done within 99% of it within vertically integrated companies, or single vendor companies, meaning the company building the chiplet is also building the heterogeneously integrated design. So they're building it for their own use. They're getting their own advantage of this modularized approach. They're not sharing those chiplets with the rest of the world. That probably, they would see that as a competitive threat. So that's where we see the vast majority of these heterogeneously integrated designs happening are in these large semiconductor companies in a closed environment, in their closed ecosystem, their own internally, only internal to their particular company. So that's great for them. If you're a large semiconductor company, it's a great way. It gives you more flexibility in the architectures you can design and all those, the great things that associated with chiplets. But it doesn't really, address the rest of the world. And so that was the question, what needs to happen to commercialize chiplets? What needs to happen before I can go to whoever's going to provide them, whether it's like a DigiKey or an Arrow, or whether it's an IP provider like a Cadence, or whether it's a foundry like TSMC. At some point, someone will have to, and people are looking at different business models for whether or not having this library of chiplets makes sense. So coupled closely with that are standards, of course, as I talked about. So there are standard bodies looking at this, trying to come up with different standards. They've been focused a lot on the communication uh, interface between the different chiplets. The DARPA CHIPS program had a vision of a single communication interface between, chiplets. I don't see that as reality. We don't have a standard packaging factor, so you can't build a chiplet that's going to necessarily work on, if you put a 55 micron pitch on it, it's not going to work on the laminate substrate. So then those people don't, have to go to a different chiplet. You don't know how big the design is going to be. You don't know whether it's going to be 3D stacked. There's lots of, there's lots of factors shown in the chart on the right, upper right there, that come into play when you start thinking about, okay, I'm going to actually build, fab, and store, in a warehouse these chiplets. Who do I, what do I build it for? Well, I don't know the packaging. I don't know how far it's got to commute. I don't know my power requirements. I don't know bandwidth requirements. There's lots of different things that you don't know about. So you end up basically creating a chiplet that's over designed. That means the IO are too big. It uses too much power. The form factor is bad. So there, it's a very challenging world. There's, in my opinion, going to be no way you can come up with a single communication protocol for all chiplets. In my view, it'll be like a PCB world where I have memory standards like DDR4, where I have serial interface standards like PCIe. So there will be a grouping of standards that are developed that work across different packaging types that are high cost, low cost, different bandwidth, all those types of things. Is my opinion of where that's going. So there are different working groups looking at that, talking about the different communication standards. The open compute people are working on a standard called bunch of wires, or BOW. Xilinx they've opened up their HBI, and Intel opened up license-free their AIB bus. So there are emerging standards, and I think it's going to be a few of those standards as we move forward. So, and then the last part of this, a couple more points I want to make here. So, these things have to be built and stored in some sort of warehouse. Who's going to do that? Is that going to be an Arrow, a DigiKey? Is it going to be a Cadence? Is it going to be a Foundry? Unknown. There are, I would say the general consensus is the IP people are not real keen right at this moment about building warehouses and storing these chiplets, and putting them in a catalog type of thing. Does it make sense that foundries have it? Maybe, if you're going to a foundry and they can provide you a library of chiplets that you can use to integrate with the wafer they're going to build for you, you could certainly make a case for that. But these are all ongoing discussions. There are no final answers to any of this at this particular moment in time. And then, of course, the last one there, as I mentioned, PPA, power performance and area. So this is, if you're an SoC designer, this is all you've been thinking about for the last decade plus. We know there's going to be compromise with PPA, and the question is, how big a compromise? And so there will continue to be more and more when you can't compromise and you need, the best PPA you can get out of a design. And there will be designs that are, can sacrifice a little bit in power performance and area, and they might move more quickly to a chiplet-based, heterogeneously integrated architecture. So, any questions on that section? Next, we're going to talk about design challenges, and then finish up with design flows. And we'll have to see.
Yep, let's see, John. I think we talked about those. Let's. Okay, so you talked about the library of parts for heterogeneous integration, and the question has been, hey, SIP has been around a lot longer than HI, so has there really been anybody who looked at it from a library perspective? I mean,
yeah, I mean, so SIP is different, right? Someone's already built. It's a chip. It's not a chiplet, so it just happens to be an unpackaged chip, right? Whether it's an FPGA, whatever it is, it's being built. You're just taking the packaging out of it and integrating the bare die. So it's a little, the chips, that's a full chip. That's not this concept of, a certain, a specific IP functionality. Now, that said, Cadence, for example, we do have what we would call chiplets available. They're mostly IO, they're basically die-to-die PHYs. So, you're starting to see some, um, level of chiplets being available for IP providers today. It's not a part you buy off the shelf. It's more it's more closely associated with like a soft block, because you have some flexibility in how you configure it and build it. So it's slow. It's I think that's what's going to happen. There's just going to be this slow rollout of people providing things like IO. We see things like memory, that type of stuff, and then hopefully it picks up steam. And I think that eventually it will go there. It's just whether that's next year or 10 years from now.
Okay, great.
All right, let's talk about some of the challenges. And again, we're limited on time, so I don't have time to talk about every single challenge. But I will start with this flow. So for some reason, the perception is out there with a lot of SoC designers, at least the ones I talk to, that moving to this world of packaging, this world of heterogeneous integration, is going to make their job easier. It doesn't. Design does not get easier when you go to heterogeneous integration. It gets harder. It gets a lot harder. You go from designing a single monolithic thing to this system level type of architecture. As I said, with 3D stacks, thermal comes in. You have to worry about things like stress, mechanical types of issues. So you have to deal with everything you've had to deal with over the last several decades, as we've moved from, very simple designs to more complicated SoCs. But the point I want to make with this slide is, for people out there that think, oh, it's my mostly SoC designers, that my job's going to get easier because I'm doing packaging now. It doesn't. It's going to get harder, and there's more capability you need in your flow, more expertise you need on your design team, and we're going to talk about those bits coming up here, at least from a high level in the next few slides. So, number one, we've been talking about throwing out this term co-design for at least 2 decades. It has different meanings to different people, but as we move to this world of heterogeneous integration, there has to be seamless, and I mean seamless, co-design between the analog and digital IC teams, as well as the package design teams. No more throwing something over the wall to the package design team and expect it to get implemented and the design to work. Those days are over. As you move into heterogeneous integration, you have to have design teams and design flows that allow a seamless collaboration, design sharing between the two different worlds. And one example of that is the picture on the bottom there. So, this is this is just showing something real simple, but this is the way, the next design tools, next design flows need to look. And so you need to have different views. Even if you have an environment that allows you to bring in the chip and the package together, you have to be able to do things like show the package or substrate designer the view they're used to, which would be the picture on the left, so that they can see down to the transistor devices on the chip that they're integrating to, or chiplet, and they see their package connections as well, and they see the orientation of the chip, in this case flipped and rotated. They're building the substrate, so that's how they need to see it for the purposes of editing and everything else. And then the picture on the right shows you the chiplet designer's perspective, which is different. The packaging isn't maybe as important to them, the chip is. So you'll see, this is the same exact design. The design tools need to say, okay, I'm looking at the chip now. So now I'm looking from top metal layer down. It's not flipped. You don't design a chip, you don't place and route a chip as it's being flip chipped. The flipping happens in the packaging stage. So you see everything from the top metal layer down. And so this, with the orientation of 0, so this gives you the view you're expecting from an SoC designer's perspective. So this is kind of the baseline. From this, now I can do my co-design, move IOs around, look at different coupling between the top metal layer of the chip and the top metal layer of the package, those types of things. So this is the type of co-design platform that I think is going to be, a key component to moving forward between to create these heterogeneously integrated designs. Again, is really, tight collaboration platform between the packaging and the chip design team. So of course, a very tight ECO loop with that as well. So that's kind of a high level, view. Looking co-design, we can spend 2 hours just talking about co-design. We don't have the time for that. The important thing is co-design will be mandatory with these next generation of designs. Another kind of gap in the flows as we look at them today is the fact that this term ADK, or assembly design kit. So this applies more to the ecosystem. It applies, the chip designers on the call, that they know what what a PDK is. Most chip designers wouldn't even start a design without a PDK. It gives you the libraries. It basically gives you, step by step everything you need to your chip and have a high confidence in it. The people in the packaging communities haven't had that in the past. That it's just been maybe a design rule manual and a couple of emails saying you should do things like this or do things like that. So that needs to change as we move certainly to these silicon-based packages. We need this thing of this term being used today, an assembly design kit. And so this slide just talks about some of the attributes of a design kit, things like tech files, the package level libraries. The A stands for assembly. So if you're putting a bunch of chiplets down in a CAD tool, I can abut them right next to one another. And the CAD tool, if I don't have a rule to check for that, it'll let me do that. However, if I happen to squirt underfill or anything like that under those chiplets, I won't be able to. I won't be able to assemble the design, at least in an automated fashion. So assembly rules are really the key. It's the reason it's an ADK, not a PDK. And they help, tell the layout person, give them feedback on, chiplets being too close to the edge of the interposer, being too close to, some other mechanical obstacle, whatever it might happen to be. All of those rules that are dictated by the pick and place equipment to a large degree need to be part of that assembly design kit as well. Other things that are important, compliance kits. These just make it easier for the people that have to validate that the chiplet to chiplet interface from an electrical perspective. Looking at things like jitter tolerance and loss in the path, and making sure your eye is big enough if it's differential signal. All these electrical factors that are part of the spec for any communication interface you need a streamlined way of validating those when you go to this world of multiple chiplets. And then the last two things here, rule decks, that's pretty common in the world of semiconductor design. It's brand new to the world of package design. We'll talk more about that. What we're used to in the package design world are more manufacturing rules, because we typically go out to board houses because we're designing laminate substrate. So anyways, I'm doing a talk on this at the upcoming IMAPS conference, the details behind what an ADK should look like. So if you want information, feel free to join that event. So now we're going to talk about design flow challenges for the substrate designers. So if your background is you've been designing BGAs, LGAs for a long time, and you're now transitioning this world of heterogeneous integration, what's new to you? And as I said, a lot of this is based on package design. So the good news is there's not a lot of differences. But there are enough, and it mostly has to do with the manufacturing output and then the verification of that manufacturing output. So if you're building something in silicon or an ultra high density RDL type of process, anything that's being built with a silicon process, you're not outputting Gerber anymore, you're outputting GDS data. So whatever layout tool you're using has to be able to output not only Gerber for the BGA that the interposer sits on, but it has to also output GDS data. And it has to be, accurate, because GDS data doesn't know what a circle is, for example. So you have to approximate with using arc vectorization algorithms and those types of things. And the most important part is that manufacturing output is going to an IC foundry. And so there are requirements for checking, making sure it's DRC clean, making sure it's connectivity clean. There's a lot more sophistication with metal fill, metal balancing, outgassing, all those types of things as you move to a silicon process. So it's very important for package designers to understand that, you're going to need some new capabilities, a little bit with the layout and being able to create, different types of fillets as shown here, be able to do more advanced outgassing and thieving patterns, and lots of little details that we don't have time to talk about today. But more significantly, you need to be able to output to an IC or mask level physical verification tool for DRC, LVS, and in some cases, smart metal fill. So this is a big change. If you're coming from the package design community used to outputting Gerber, that's going to change. You're going to need a tool that supports this. If you're coming from the SoC design world, there's challenges certainly if coming from them. I don't have time to outline all the challenges, but this is the first challenge that SoC designers run into is, okay, I'm building multiple chiplets now. How do I manage that system level design? How do I manage the connectivity, and the net list that ties together these multiple chiplets? How do I manage the stack? How do I, optimize the design for the pinouts of the BGA? How do I, create my array of hybrid bond pads? How do I create my array of TSVs? So the biggest gap today in most SoC design tools is, they're used to design a single device. Now you're having to integrate multiple devices, multiple chiplets. So there's a need for a top level design aggregation, planning, and optimization tool, which is really the source of your connectivity or LVS checking on the back end of the design. So you need to look for a tool that has capabilities similar to some of the features that I've mentioned on this slide. And then, of course, we can't forget, we have to be able to validate this thing electrically, thermally, timing-wise, everything else. So here again, the world of EM extraction comes. So if you're an SoC designer, you mostly use tools that just do RC extraction, kind of a table-based way of looking at layout parasitics. When you move the system world and off of the chip and into interposers and packages, you need more advanced electromagnetics tools in there, and you need InDesign, and you need sign-off level tools. So you need tools that are planar in nature that can give you the inductance of a coil inductor in a minute or two, and then you also need a finite element full wave EM tool for signing off more complex types of structures. And so you need almost a suite of different electromagnetics, RC, EM extraction capabilities, depending on whether you're working on chip, off chip, system level, whatever it might be. And then you need to perform more types of analysis. So, you need to look at heat transfer, obviously in a 3D stack. You need to look at power. If you're looking at power, you better be looking to the board, because the power comes from the board to your chip. So you have to model the power, the VRM from the board through the package or the interposer up to the chip if you really want to know what's happening power delivery wise of that. So it's, again, a system level problem as you move into these world of multiple chiplets. Fluid dynamics comes into play, CFD, computational fluid dynamics. So you need to look at airflow, and here again, thermal. If you don't include the board when you're doing thermal analysis, it's kind of a waste, because the board is your biggest natural heat sink in the entire system. So again, another example of needing to move to a system level design approach when you start to do all your electrical and thermal analysis. And of course, it doesn't hurt to have all that integrated in with the design flow and design tools that you have. So those are some of the high level challenges. We could break each one of those down into its own topic, but we're running out of time here. So I'm going to just finish up real quickly with the last slide, and I'll hopefully have a minute or two for any questions. So We're going to finish up with talking about some design flows. So here at Cadence, just as a reference, we break these types of these heterogeneously integrated 3D stacking flows into 3 tiers: a planning and optimization tier, and then leveraging the tool that makes the most sense for the implementation, whether it's a digital chiplet, an analog RF, even MMIC can be handled in the flow. The packaging, traditional BGA, LGA that these interposers and 3D stacks sit on, the board that all comes into play, and then having that tightly coupled, as I said, with all of the EM extraction, signal integrity modeling, power delivery modeling, both on chip, off chip, thermal, both self-heating and mechanical parts of thermal, using computational fluid dynamics to look at airflow and those types of things. So real quickly, here's an example of the different components that you would need in a multi-chiplet flow, and I've kind of got kind of a mixed signal example here. So you have to have tools, obviously, design each of the chiplets, and from there, it certainly helps to have a single system level library. So again, here's that word system level. I'm not designing a single chip. It's not a single library. I need to have within my library all of the off-chip components, and that should ideally be in a single library. From that single library of chiplets that you've created, some sort of way to capture that top level design. I'm showing a schematic here. From that top level design, being able to have a co-design feature between that logic and the physical design. The first thing most people check for in a 3D stack is the thermal, so that needs to be tightly plugged into it. And of course, we have to be able to model the performance of your multi-chiplet design. So you have to be able to have access to the EM tools that I talked about, that it can work on chip, off chip, full system level, extract those layout parasitics and feed them back to your golden source of logic, and in this case, the schematic, so that you can simulate simulate accurately the performance of your multi-chiplet solution. Of course, you can't forget the board in that, and then being able from that platform to build test benches and simulate the functionality of your system. And then last but not least, being able to take the layout data, being able to go out and doing sign off with a physical verification tool. So these doesn't show all the steps within the design flow. I didn't talk about timing here. That's another topic. If you talk about STA, because you're an ASIC designer, SoC designer, that goes away. You're dealing with passive fabrics here. So silicon interposers and laminate substrates, there are no device layers. So I can't insert a buffer or make a buffer strong to meet timing. All I can do is wiggle lines around. So timing becomes more about a constraint driven routing to match signals and those types of things as you move forward. So I'm going to wrap up here real quickly with a bit of a riddle or a tongue twister. So the most common 2.5D design out there today are HBM stacks next to some processor. And really what it is it's taking a board and taking the DRAM that were placed on some DIMM card that were side by side, putting those into a 3D stack, and then moving them up onto an interposer. So based on what I talked about today, is that closer to a SIP, or is that closer to a heterogeneous integration design? I'm using that term that people are using today. To me, it's more of a SIP. There'll be probably a ton of people out there that disagree with me. I would not call this heterogeneous integration under today's definition, because I'm taking a board and I'm simplifying the board. So I'm taking stuff that I already did at the board level, and I'm just moving it into a package level to improve performance, bandwidth, all those types of things. So I know a lot of people out there would call the design in the bottom right there a heterogeneously integrated design. I would not. And then to wrap up, we're for a lot of us and more to come, we're in this world more than more where it's all about packaging and leveraging the tools and the expertise that we've had in system applications for a long time now. And that because we're moving, there are going to be challenges in these new flows. Things are changing. The package designers are going to have new challenges, mostly from with plugging a physical verification tool into their flow, and the IC designers are going to have their own challenges with top level planning and those types of things. So we believe you're going to need new expertise, new design tools, new design flows as you move towards this world of more than more. And thank you for your time. That wraps up, concludes my my talk. Thank you.
Thank you, John. Really excellent talk. There's a whole bunch of questions, and we'll address as many as we have time. We'll stretch a little bit on the time, but the first one, and I think it's probably the one closest to my heart, you talked about co-design, but you didn't really say the word test much at all in your presentation. And do you see, like, the ADK would probably have some things about protocols and the test features of it, but does there need to be a TDK, that the tools are aware of the challenges of test?
Yeah, so yep, so there's a great question. So there are, it really depends on whether it's stacked three-dimensionally or not, right? There are different as soon as you start stacking things three-dimensionally, and I want to test that third chip up in the stack, but it's not touching, the interposer or whatever, so I have to have elevators to go in and test that. So there are, test standards being developed for 3D stacks that are going to come into play here. I think that's the biggest kind of paradigm change when it comes to test is really when we move to take those chiplets and start stacking them three-dimensionally. But yeah, there are, it depends on whether you're integrating on a thin film laminate or a silicon interposer. The test structures, test specs will be different for a lot of those different applications.
And do you see in the chiplet space the IP block vendors offering advanced DFT? I mean, how cognizant are they about how the chiplets need to behave from a test perspective in the system architecture?
That I would probably bring in one of our test experts to talk. We talk in specific detail about that. My background's not in tests, so right. I'd get myself in trouble if I go too much deeper on this.
Okay. Okay. And okay, so switching back to the ADKs, I'm assuming they're in, but the person who's asking the question is saying, shouldn't the thermal and mechanical design rule guidelines be included in the ADK? That's the intent, correct?
Yeah, I'm sorry, I did have that. The ADK under libraries. Let me see if I can bring that back up real quickly. Share. Yeah, so things like, so if you look under design libraries there, I have footprints, these are things like the surface mount capacitors that are going to go on your design. If it's a bond wire attach, you're going to need the three-dimensional profile. As I said, you move this world, you're working with microbuffers and IOs, so you need switching behavior of those IOs, and absolutely you'll need some thermal models for each chiplet will need to have its own thermal / power model associated with that. So yeah, I just have all that under the category of design libraries, and maybe I should break that into a separate category. But absolutely, having that those models is going to be critical to a good ADK.
Okay. Okay. And just a reminder for people who haven't taken the poll, if you would take a moment just to give John some feedback as we go here. So then another question, and I think the gist of this one is, substrates are becoming more complex than just wires. I mean, there's both active substrates and passive substrates, and there's embedded passives in them. Is there a roadmap for the capabilities of designing substrates? I mean, I'm assuming if it's a truly active substrate and it's silicon, you would design it like an IC in a full-blown suite of tools. But, you know, there's this threshold of things that are probably a little simpler, but much more advanced than a traditional printed circuit board.
Yeah, so certainly from a silicon interposer, if that becomes active, that means you have device layers, you have front end line of processing going. So in that case, it's a chip, it's an active chip, and it would be designed in a traditional IC type of layout environment. If it's a laminate an organic / laminate substrate, there are no such thing as device layers. Everything is passive on that. Yes, you can build cavities, you can do embed die, that type of thing, but there is no way to add, mostly speaking, there's no way to add logical functionality to a passive BGA substrate like you could with an active silicon interposer, where I can, I have transistors and things I can build logic from. So I mean, that's the thing, right? The main two types of packaging technology people are looking at are certainly, thin film build up BGA types of substrates, and of course silicon interposers. I would say the third that I hear is probably glass. But yeah, they'll each, that's where the tech file comes in, right? The tech file is really, okay, this thing is made of this material and it has these electrical properties and it has this thickness and it has this many routing layers, and all that type of thing is really driven by the tech file, which is the first component in a PDK, ADK.
Okay. You showed on some of your slides, and this may be a teaser for a future presentation, but can you speak briefly about co-packaged optics and, design challenges, where they fit in here and where you see it?
Oh,
Sorry, that could be a whole hour.
That's an hour. That's a separate talk for a separate day. That's we don't, right, because that's all over the map too, different depending on how far you carry the if it gets carried the waveguides onto the packet. Anyways, yeah, I think a separate session for that.
Okay, well, we should definitely put that on, because that is a very popular idea. So let's do one more. How does the 3D stack of chiplets impact the substrate design? Does the substrate end up having more layers, smaller feature, smaller body size than the packages, the substrates people are currently designing?
No, I don't think so. I think, because it's from the package perspective, it's about, in the case of a 3D stack, it's simply about the connections to the bottom die, right? That's what the rest of the stack, those are, inter die connect. They're just staying chiplet to chiplet, right? They're not. That's the idea of the 3D stack. Taking maybe SRAM and stacking it on a processor, right? It's just that SRAM just talks to on that chip. It doesn't leave that chip and go on to the package and out to the PCB, right? So if you think about packages, all about bringing the power from the PCB on through the package into the chip, and also about bringing the I/O, the system level I/O, just the signals that are going to communicate out to the board world in a fanned out pattern that board designers can, in geometries board designers can work with. So I would say, no, as soon as you go 3D stacking, the three most important things are thermal. I mean, that's you've got to get that sorted out long before anything.
Great. I thank you, John, for an excellent presentation, and thank people for joining us. Let me throw this up here. So a reminder, our next semiconductor industry speaker series will be on Wednesday, March 31st. Tom Green will talk about the mil-spec hermeticity testing of class 3 medical implants. It should be an excellent presentation, so please join us then. The slides from today's presentation and the recording will be available on the MEPTEC website, meptec.org. You'll get an email letting you know it's there, or you can subscribe to our YouTube channel and you'll get notification as soon as the video is posted. So I want to thank John again and thank everyone for attending. And I will wish everybody a good day. So thank you.